Whenever you're ready, Tom.
Does that look okay to everybody?
Perfect.
Great, I'll go ahead then. So yes, thank you very much, Marcus and Richo, for organising, and I'm going to talk to you a little bit. This is kind of a continuation from Jason Koskinen's lecture yesterday, where he discussed the IceCube Neutrino Observatory and how neutrino oscillations can be measured there, and why you might want to do that. And here I extend that further to looking not just at oscillations in our current understanding of the free neutrino paradigm, but what other potential new physics scenarios neutrino oscillation measurements might reveal. So just a brief introduction to why you might want to look for new physics. We have, in general, two very powerful models that help us explain a lot of what we see in the universe, this being the standard model, which describes particles and their interactions at the microscopic level, as well as general relativity, which describes how gravitation works at the very large scales. But despite the remarkable success of these theories, there are many open questions still remaining, and in particular, in how these two forces relate to each other, or these two ideas relate to each other. Some of these questions, I've put a few of them down here that are specifically that can be addressed by neutrinos specifically. There are many more than this, but these involve questions like, why is gravity so weak? Is gravity a quantum force, or how do we describe gravity at a microscopic scale? For example, in a black hole or in a particle interaction or at the start of the universe. What gives neutrinos mass? We still don't know this, though we know it has it. What are dark matter and energy? Obviously, absolutely huge questions in particle physics and cosmology. In general, are there new particles and forces? There are various anomalies, especially in the lepton flavor sector. And another big question is, where is all the antimatter in the universe? We seem to live in a universe made of matter and not antimatter, but we don't really understand why. So there's a lot of things still for us to understand, despite the success of the standard model and general relativity so far. So why specifically neutrino oscillations is a place to look for signs of new physics? So neutrinos propagate as a superposition of, well, at least three, to our knowledge, currently three mass states. And this was covered, I believe, already by Jason yesterday. But the idea here is that when you're observing a neutrino propagating, you're not really observing a single state, but instead this superposition of three states simultaneously. And this superposition effect, combined with the non-zero masses, gives rise to this peculiar macroscopic quantum phenomena of oscillations. This is interesting from a new physics perspective, though, because potential new physics could modify or degrade these oscillation effects. So the superposition may be modified, and what this really means is your neutrinos are acting kind of like a tiny quantum interferometer. So any impacts on these as they travel will produce potentially different oscillation signals, and this is something we can search for in data. There are some other properties of neutrinos that also make them ideal for looking for new physics. So one is that they can travel very, very large distances, even astronomical, cosmological distances, which can allow potentially weak signals to accumulate over these very large distances. I think you might eventually measure. There is also the question of the energy of these particles. Neutrinos are available in high fluxes at high energies, even up to PeV energies, and this potentially opens some access to high energy scale physics. And because neutrinos are not really affected by the electromagnetic and the strong forces, this avoids kind of diluting down or sort of masking some of the other potentially much weaker new physics we can search for.
Tom, can I interrupt you for a second? There was a question by Aman. What is real and imaginary oscillation?
So oscillations themselves are a real property, but the quantum wave function has both real and imaginary components. So just in terms of complex numbers, and so when you consider any wave function, you really need to consider both the real and imaginary components. And eventually, when you calculate a real observable, in this case oscillations, then you take you eventually project and square anything in the same way as a matrix transition element. You always end up with a real quantity that you observe, but in the underlying quantum wave function evolution has both real and imaginary components.
Thanks.
Okay, moving on. Feel free to stop me at all with any questions as we go. So I've tried to make a case why neutrino oscillations are a good place to search for new physics, and in particular, I'm going to be talking about the oscillations of neutrinos produced in the atmosphere. So, as you probably already know, there's a huge flux of cosmic rays constantly bombarding the Earth from some known, some unknown sources. These cosmic rays, as they, for example, protons, as they slam into the atmosphere, they produce showers of interactions, and which produces a flux of high energy neutrinos. And in a very large detector like IceCube, where we can observe very high rates of millihertz, which roughly means you're seeing neutrinos every 15 minutes or so. So very high rates compared to most other neutrino detectors, and you observe them at very high energies. And so there's this great natural flux. We don't have to build a beam. The universe provides these for us. And the neat thing is that these neutrinos, as they propagate from where they're produced in the atmosphere, they can cross the entire distance, the entire diameter of the Earth before they're detected, for example. They can go straight through the Earth in general because neutrinos can have such great penetrating power. Though interestingly, at high enough energy that even the Earth is able to absorb them. But at GeV energies, neutrinos could be expected to oscillate as they cross the Earth. So we've got a natural source of oscillating neutrinos we can try to measure. And just to sort of orient people on the parameter space here, so the main dependent variables in terms of neutrino oscillation measurements of atmospheric neutrinos are the energy of the neutrino and the travel distance. And for an atmospheric neutrino, we can directly relate the travel distance to the incoming zenith angle. Something coming from directly below you has come through the Earth, something coming from directly above you has come from just 10 kilometers or so up in the atmosphere, and with everything in between. So this is what oscillations look like in the atmospheric parameter space. On the energy scale here, at this lower sort of GeV and below energies, you have this strong oscillation patterns, but then no oscillations, basically at high energies, until your neutrinos become so energetic the Earth absorbs them. And so if you see any oscillation signals out here in most of this kind of greater than approximately 100 GeV energy region, this is something we can't explain with neutrino oscillations as we currently understand them. And this would be a pretty strong indication of new physics. So I believe IceCube's been covered in quite a lot of detail by Jason's talk already. All you really need to know from this is that IceCube is a very, very large detector, and so it's the world's highest energy and highest statistics atmospheric neutrino detector. And that's what's really important about this detector for what I'm going to tell you from now on.
Can I, before you move to this section, there have been two more questions. One is by Trisha. Why muon to tau neutrino oscillation channel particularly is dominant at IceCube?
The reason is that the atmospheric neutrino flux is dominated by muon neutrinos, particularly at high energy. So this is mainly because it's coming from pion decay, and so you have this flux, or initially pion decay. Later, there's also a component from muon decay. But so you start with mostly a muon neutrino beam at high energies, and because we know that the atmospheric mixing angle is close to maximal, so approximately 45 degrees. This means that there's a very strong mixing between muon and tau states. And what that really means is that if you start with a lot of muon neutrinos, after long enough time, you'll have, roughly speaking, an equal mix of tau and muon neutrinos if you're in the right energy space. There's also electrons in the beam, but it happens over the energies, and basically the electron transitions you'd need to observe at longer distances than the Earth's diameter to really see much.
Thank you. And there's one more question by me here. Is there any, so I guess this is a follow-up of the imaginary oscillation part. Is there any significance of having imaginary part in neutrino oscillations?
There is significance in it in the sense that if you neglect to take this into account when you are computing your neutrino transition probabilities, you'll get the wrong answer. Essentially, when you're looking at a complex number, the number is complex, and it's you basically are required to treat both the real and the imaginary components. So something you have to take into account, but it's I wouldn't say there's a more deep interpretation than simply this is a complex wave function that needs to be basically projected out to give you ultimately a real observable.
There's of course also the CP phase, which is a complex phase.
Yes,
so,
that's also an interesting question. Actually, that so in terms of the actual mixing of your neutrinos, so there is if there is a complex phase related to that, as Marcus mentions, then you can potentially have different oscillation properties between neutrinos and antineutrinos. which could then relate to this issue of the matter versus antimatter asymmetry of the universe. This is a very interesting question. It looks from recent measurements of accelerator neutrinos like there is CP violation in the neutrino sector, and probably quite strong neutrino oscillation, though it's not, this isn't a discovery yet, and there's some tension in that field, but this is a very interesting observation, but it's not something yet that atmospheric neutrinos have been able to contribute much to. So I'm not going to cover that here, but it's a very active and crucial part of the neutrino, sort of the global neutrino physics program.
Thank you.
Okay, moving on. So what I'm going to do now basically is cover a number of different new physics topics that are kind of what I would call sort of hot research topics, things that are actively being worked on by IceCube physicists, and address some of the kind of the questions that I outlined that we have in physics as it stands. So first, this is non-standard interactions. The idea here is that as neutrinos propagate in matter, there is an effective potential experienced by them due to coherent forward scattering of the electron neutrino component of electrons. This is not new physics. This is well-known effects. The MSW effect is one of the main sort of examples of this. And so what this really means is neutrinos propagating in matter experience this additional potential, essentially an effective mass, and so matter can affect neutrino oscillations and modify oscillations. What that also means is that any new force we don't currently know about could also produce a matter effect. And so not necessarily just between electrons, but even between quarks, for example, neutrino quark interactions that we currently don't know about. And so one nice and quite general way to search for new physics is to look for any unexpected or non-standard neutrino matter effects as neutrino propagates through dense matter. The phenomenology people tend to use in this when treating this is to write out this a very generalized modified potential matrix. The idea here is that, without going into too much detail on this, the idea here basically is just to write down the most general possible potential that new physics could potentially realize, and then the different elements of this matrix correspond to different potential new physics cases. So, for example, lepton flavor violating or universality violating, where universality means that the interaction was basically the same strength for the different flavors of lepton. In terms of atmospheric neutrino oscillation, so the NSI depends on the density of the matter traversed, and so neutrinos crossing the very dense Earth's core are going to potentially produce the strongest signal. There's a very rich phenomenology here, depending on what exactly what type of matrix you're testing, which depends on the underlying nature of the forces. But two example cases here. These are neutrinos basically crossing through the Earth. These are muon to tau transition probabilities as a function of energy. You can see one example here for universality violating NSI is what you change here is essentially the amplitude of these oscillations here. So you'd expect basically to weaken your standard oscillation effects. Whereas for these flavor changing cases, you also produce more complex effects where you can also shift the frequency of these oscillations. And so there's really quite a rich phenomenology of here, but it's something you can test with data. And it's something that a whole range of experiments globally have done, in particular IceCube recently, but unfortunately no evidence has been found yet of these non-standard interactions, even testing a whole range of these different matrix elements. And what this really means is we have not yet found any such new physics. So any new physics along these lines must be weaker than we currently have sensitivity to. And we'll keep searching with more and more data as it comes in.
Tom, there was a question by Aman. How do you get the epsilon matrix?
In short, there are ways to derive this from, what you can, for example, try to derive from first principles from some new theory, any way you want the format of this matrix. But what's instead done here is essentially to assume, I think, a 4-point contact interaction and a vector propagator, and then you basically just write out the most general thing that could possibly exist here. So you have basically, it's 3 by 3 because you have 3 neutrino flavors. And so you just end up with a bunch of terms here. The reason for this slightly complicated structure on the diagonal is because all neutrino oscillation phenomena is invariant under a global change of phase. So you can always basically subtract a number from the diagonal here and to reduce your degrees of freedom by 1 in exactly the same way that neutrino oscillations are only sensitive to masses and not these squared masses or mass differences and not masses directly. And so this is why you end up with this negative signs here, and the 1 here is the standard matter effects. So basically, if you assume a 4-point vector interaction, this is the most general thing you could possibly write down. And then it's an interpretational question how to relate this to new physics models later.
Thank you.
Can I ask?
Yeah, of course. Go ahead.
Yeah. So actually, in this cartoon that you have shown, that this is the standard, and the right one is the non-standard. So I mean, the interaction is with the standard particle. Then why do you call it as a non-standard interaction? I mean, what are the guiding forces to call this right part of the cartoon as a non-standard?
So the reason this would be non-standard is because you would need this would only take place if you had a new force that produced some interaction that was importantly either lepton flavor violating or lepton university violating. So there are already, for example, weak interactions between D-type, U-type quarks or electrons and neutrinos. But the crucial difference here is that you need something that has a kind of a relative difference in the effect between the different flavors. If you don't, then you're essentially subtracting a global phase from the system, which is the same thing as I mentioned on this diagonal previously. So what's non-standard about this is you need a new force that does not behave the same for all flavors.
Okay, so new force in the sense means the coupling would be different from the standard, right?
Exactly. So you could imagine a new propagator, like maybe for the weak force, you have the W and Z bosons. Here we're talking about a new particle being a propagator in this force. So maybe a new heavier boson, for example, or something along those lines. So there's a new force carrying particle being exchanged between neutrinos and matter.
Yeah. Okay. So I mean, what are the guiding? I mean, there must be something theory behind this. Sorry. Okay, I will talk about later. Thank you. Thank you.
Okay. Yeah, feel free to ask later as well. We can get to that.
Maybe one quick follow-up question here by Jamie. Can the epsilon parameters also depend on energy or other parameters?
I assume you could construct a model where they did. They're not typically imagined to here, and the standard matter effects do not. But you certainly could imagine constructing it. I've not seen that addressed. So to my knowledge, I've not seen a model constructed that way. There's probably a good reason why, but I must admit I don't know why that's never considered.
Okay, and one last question on this topic. This really seems to be very interesting. Is it possible, so this is a question by Anthony, is it possible that an epsilon with complex phase has the same effect as another epsilon?
Could it produce the same effect? I don't think exactly the same effect now. So I don't think there's a direct degeneracy between these in the same way. Because if you take, for example, epsilon E mu, for example, and then epsilon E tau, I mean, this one is controlling transitions between, or basically difference in the interaction between electron and muon flavors, and this one is between electron and tau. So I don't think you can directly produce the same effect easily there. Maybe, I guess, you could do something by doing E to tau versus E to mu, just because of the maximal mixing between mu to tau, you could produce some sort of similar effect over long range or something like that. But I don't think these parameters are complete. There's not any complete degeneracy between these two parameters, really, although in any particular experiment, it's possible that there is degeneracy. So for an IceCube, for example, we're not really sensitive to the complex phase, as you mentioned, because we can't really distinguish neutrinos from antineutrinos. So there is a kind of, there is some degeneracy for us there, that's not inherent to the model, it's a limitation of our detector.
Yeah, I mean, as part of the Hamiltonian, it has to be a Hermitian matrix, so that introduces some relation there between the basically top right and left bottom. But yeah, otherwise, I think these are general. Okay, I think we should move on in the interest of time. Sorry, if there are follow-up questions, maybe Tom has the time later on to join us for the discussion session.
Okay. Sounds good. So I'll move on. I think we're a little bit behind time, so I'm going to move a little bit quicker through some of the next topics. But so either feel free to ask questions, or indeed in the end, if we run out of time, as Marcus says. So the next topic I was going to come to is sterile neutrinos. So the idea here is that in general, our general understanding of the weak interaction, only left-handed neutrinos are produced. This is, or right-handed antineutrinos. This is a consequence of parity violation. We don't have a good theoretical understanding of why the weak interaction violates parity from any kind of underlying theory, but it's an observable fact that it does. But But right-handed neutrinos could in principle exist. They just wouldn't be produced in weak interactions. They would only experience the gravitational force or some currently unknown force, and that's why they're often referred to as sterile neutrinos. But they're a topic of a lot of interest because they're typically required in many models that seek to explain why neutrinos have mass, which is one of the big open questions in the standard model. The way to search for these is not to try and directly detect these particles in general because they're sterile, then they're not interacting with anything, you can't directly see them, but because they are mixed with standard active neutrino states we know about, they modify your oscillations in a way you could potentially measure. And so what experiments have been doing a lot over the last few years is they basically look at extended mixing scenarios with more than 3 neutrinos and try to test if that's consistent with our data at all. And normally people look for a single sterile state, which just basically keeps things a bit more manageable, although in principle there could be any number. In principle, they could also be a pretty huge variety, virtually any mass really. You can't go too massive, but many orders of magnitude above GeV, for example. But there's been a lot of attention on roughly EV squared mass splitting sterile neutrinos due to various anomalies in the short baseline and reactor measurements. In IceCube, though, we have quite a unique signal. And the idea here is that if you have this mixing between active and sterile neutrinos, you're actually able to observe another kind of non-standard matter effect, not the same as I was mentioning before, where you basically have a resonant disappearance of muon neutrinos, so resonant transitions of muon neutrinos to sterile neutrinos, and hence no observation in the detector. And what you'd expect to see then is kind of a small region with a depletion or complete deficit even of muon neutrinos in your detector for around TeV core crossing neutrinos. So a very strong, unique signal. Alternatively, a sterile neutrino or a very massive sterile neutrino would produce additional high frequency oscillations that would be kind of averaged out in your detector. So there's a couple of different channels here. But the punchline, unfortunately, like so often is the case for new physics, is that we search for both of these effects with IceCube data using very large, very modern data samples of over 300,000 neutrinos. And unfortunately, we do not find any strong evidence for either of these scenarios. So what we observe is consistent with there being no EV scale sterile neutrino. This is a strong tension with some of the anomalies that other experiments are seeing. So there's a lot of work still to be done in the sterile neutrino community. And the kind of final topic I will cover here in terms of new physics, this covers a couple of areas here, is the topic of Planck scale physics. And so what I'm talking here really about is physics at high energy scales. The idea here is that there have been a lot of attempts to explain some of the shortcomings we have of standard model and general relativity by postulating new, much higher energy theories. So quantum gravity is probably the most famous example of this, and the various attempts to explain quantum gravity with string theory and brane theory and loop quantum gravity, etc. These typically postulate some new physics, some new energy scale, often the Planck scale, which is a huge energy, so roughly 10 to the 19 GeV, or very small distances. So the Planck length or the Planck mass, you might have heard of these numbers as before. So the idea here is there's some new physics that is very strong at very high energies, way above what we normally observe. And then the standard model is essentially the low energy limit of that theory. So any of these effects are suppressed at the energies we see, but they are still participating somehow in the background. It is a frequent prediction of these theories that there are modifications of the properties of space-time, and in particular its fundamental, for example, symmetries. So things like Lorentz invariance may be violated, the CPT might be violated, and we might start to lose coherence in neutrinos. And I'll talk about these individual topics next. But the key point here is all these effects are very expected to be very suppressed at the energies we normally observe, and so you want to go to the highest energy neutrinos possible and with the highest statistics possible to search for these weak signals, and that's where IceCube is particularly powerful. I'm going to kind of cover two of these topics here. First is Lorentz invariance violation. For those who are not familiar with this concept, the idea here is that a very fundamental part of physics today is that your experimental results should be independent of the orientation and velocity of the laboratory frame. Basically, if you do the same experiment on Earth or in a rocket traveling far from the Earth, you should get the same result. However, this is predicted to be broken down in many theories such as string theory and SUSY, etc. So this is a very common. It's often predicted that this might be violated at high energies, and the kind of things you might expect if this is the case is things like an energy dependent speed of light, or indeed a preferred direction of space time. So real fundamental differences from what we currently understand. People typically treat this via something called the standard model extension. Since we're a bit low on time, I won't go through this in detail, but the idea here basically is that you take your standard neutrino oscillation Hamiltonian and you extend this to include all possible Lorentz violating operators. So it's very general, a bit like the NSI case I covered previously. And then you test if any of these operators, basically to test for the presence of these operators producing anomalous high energy neutrino oscillations, or in fact, or maybe signals in other, cosmic rays, or even precision nuclear and benchtop tests. So many people have tried to search for these effects and none have been found yet. But atmospheric neutrinos are particularly interesting because of this fact that we're observing these very high energy particles, potentially a lot higher energy than even the Large Hadron Collider or something like this. So what they're really looking for here is anomalous transitions from muon to tau neutrinos at the highest energies. IceCube performed this search a few years ago. The idea here was, as I mentioned, you can see this picture here. What you're really looking for here is some deficit. You'd expect some deficit of vertically traveling neutrinos at the highest energies observed because of these. You start to basically add neutrino oscillation effects beyond what you otherwise expect at high energies. But unfortunately, as is often the case, no such effects were observed. And so IceCube was able to place the world's most stringent bounds on higher order effects here. Skip this because of time. The final topic I'll cover here quite quickly, so I think I'm out of time here, is neutrino decoherence. This is quite a complicated topic, so I'll try and cover it a bit more quickly here. The idea here is that neutrino oscillations are generally a coherent process. The idea here is that although neutrino oscillations are probabilistic, the actual wave function themselves are evolving in a coherent way. So if you were able to directly observe the wave functions of two neutrinos of the same energy traveling the same path, they would be evolving absolutely identically. That's, however, not true if they're propagating through some stochastic medium anymore. And what you'd actually expect in that case is your neutrinos to become out of phase with each other over distance, and oscillations would start to damp. You have this characteristic damping of your oscillations. Your oscillation effects start to disappear over distance. I mentioned this happens in a stochastic background. So what is a stochastic background? And the main answer of interest here is quantum gravity. If gravity is a quantum force, then it's subject to the uncertainty principle like any other quantum force. And what that really means is the structure of space-time itself may actually be fluctuating and not at all a continuous sort of stable environment. And so neutrinos propagating in that may lose their coherence, and we can search for this damping effects. The formalism is a bit involved for neutrino decoherence because we're over time here. I'm going to skip the formalism. We'll come back to the questions if you like, but the signal really here is this damping effect I mentioned before. In terms of neutrino oscillations, what we're looking for really here is high energy damping of neutrino oscillations. If you can see here, for example, this region here is where you have standard oscillations, but actually these standard oscillations will become weaker in the presence of decoherence because you'd have this damping effect you see here, which is the blue curve, compared to the standard expectation of the gray curve. So the effect of decoherence here is essentially to weaken as a function of distance your standard oscillations, but then basically to induce these kind of exponentially decaying flavor transitions at high energies where there are previously no oscillations. This isn't in principle, this isn't strictly a neutrino oscillation as such, it's just a flavor transition still. But so ultimately you have these two independent signals, basically. Flavor transitions where there were none, and a weakening over distance of flavor transitions where you previously had seen them. And there are various ways to check these, and the phenomenology here is again very rich, depending on what you consider the energy dependence of this physics to be, etc. Basically out of time here, so I'll skip this. So I'll wrap up, and feel free to ask questions on some of these topics I've covered a bit more quickly here. So just a summary and outlook here. So there are many open questions remaining in fundamental physics. So we're far from having all the answers, and neutrino oscillations are very sensitive in particular to many of these answers to questions. For example, the higher energy scale, all these higher energy scale effects, and some of the really big questions, quantum gravity, theories of everything, this kind of thing. The atmospheric neutrino oscillations with IceCube offer world-leading sensitivity here because we have very high energies, high baselines, high matter densities, high statistics. All these, basically IceCube is always bigger than everything else in all regards, pretty much. And this really counts when you're looking for physics at new high energy scales. But unfortunately, no signal yet, but we have new generations of high statistics measurements on the way. So maybe we'll find something that was lurking just below the surface of our previous measurements. And in the future, we have both the IceCube upgrade and Gen 2 to really improve our sensitivity and take us further down this path. Okay, thank you.
Thanks a lot, Tom. That was a very nice overview of the potential of IceCube. There have been a couple of follow-up questions on various topics. My first question would be, are you available for our general discussion session later on? Otherwise, we will take the questions now. So we have a discussion session at 4:30. Would you be available for that?
It's probably best if we try and do now. I will try to be.
Okay, then we
I'll have children at home, so
yes, of course. Then we will take this now, and we will start a little later then with Olga's second lecture. So there was a question by Nora: how could sterile neutrinos be produced? Is it through a decay?
In this scenario, the kind of scenarios I'm talking about here with oscillations, we're not really talking about them being produced in a decay, but it's more that in the same way that when you produce a neutrino of a particular flavor, it's actually a superposition of many mass states. If you have these additional sterile states in there as well, you're also producing these additional states there as well. So it's essentially produced in the initial weak interaction. You could also imagine sterile neutrinos being produced by a dark matter decay or something if you had some new force, something like that. So it's, if you have some, but you need some force to produce it. Right now, sterile neutrinos only experience gravitational force, and there's no sort of gravitational decay process that we're aware of to produce a neutrino in those terms. But if you have a new force that sterile neutrinos can couple to, then you can, in principle, access them via decay channels, for example.
Thank you. And there was a question by Trisha about virtual black holes. What are they?
Yeah, so I skipped this topic a bit because of the time. I'll just jump back to it here. The idea here is that so this is a very exotic sounding concept, but the idea here is that once you consider a quantum, fields, you have, as I mentioned, you have the uncertainty principle, and if you just take the standard electromagnetic force, our quantum picture of how that operates is that although you have, let's say, an electron sort of passing, traveling through space. Around that electron, we imagine this sea of constantly appearing electron-positron pairs popping in and out of existence. This is called vacuum polarization. And this is, for example, crucial for us understanding the strength of the electromagnetic force. This is very well established. If gravity is a quantum field, then the quantum gravitational analog of that, basically the virtual particles that are popping in and out of existence are virtual black holes. So essentially you have popping in and out of existence, you have these basically fluctuating space-time curvature that you have very rapid collapses of space-time into singularities, which then immediately evaporate again. So these are black holes that exist on tiny microscopic scales and for tiny amounts of time, but constantly popping in and out of existence. They're not; these are conjectured. No one knows if these are real or not, but they're a fairly natural extension of what you might expect from a quantum gravitational force, but because we don't understand everything about, for example, information loss in black holes, we don't really know if these are a real property of the universe yet, but it's they've been conjectured, for example, as to explain, or they would be a source of neutrino decoherence, and they also would be a source, for example, of proton decay, because they would allow, for example, flavor or baryon number violating decay channels for a proton. So it's quite exotic sounding stuff. Certainly not known if they're true or not, but it is one of the possibilities of what the phenomenology of a quantum gravitational field might be.
Thank you. I see that Nora actually had a follow-up question on sterile neutrinos, but Nora, I think Joachim Kopp is also going to talk about this in great detail during this week. Maybe so this is a very good question that you ask here about the mass of the sterile neutrinos, but maybe we can discuss this in the other lecture. And then maybe one last question before we have to move on, and this is coming from Shekhar. I hope I pronounced this name correctly. So neutrino count in IceCube, there are any count effects for Earth's own rotation or the rotation around the sun, seasonal effects?
Yeah, I see what you're saying. So in terms of standard physics, I mean, you have, for example, effects from the Earth's magnetic field, and as the Earth rotates, your cosmic ray flux changes slightly. So there are in principle effects. You also just have effects where, depending on the season, for example, in a particular point on the Earth's surface, the temperature of the atmosphere varies, which means that also the the way the air shower develops and the cosmic ray varies. For example, you change the likelihood of a neutrino for example, a pion re-interacting before decaying, for example. So the particles that come out of your cosmic ray air showers depend on the atmospheric temperature, and thus they depend on the weather conditions, for example, in a given point on the Earth, which is of course seasonally dependent, though when you're observing over the whole Earth, you kind of integrate these things out in general. But there certainly are relatively weak seasonal effects there in the atmospheric neutrino flux. Of course, we're not directly sensitive for the most part to solar neutrinos, so we're not really experiencing that. But there are also new physics potential scenarios for these effects as the Earth rotates. So, for example, in Lorentz invariance violation, if there is some preferred direction to the universe, i.e. your physics experiments will give different results depending on the orientation that you place your experiment at, then of course, as the Earth rotates and moves around the sun, or in fact, in this case, it's not really seasonal, but it's more as the Earth just rotates on its axis. So it's a 24-hour effect. This is called sidereal rotations. What you'd actually expect is your experiments, such as neutrino oscillations, to actually experience slightly different effects, basically as a function of 24-hour periodic time rotations. So there are also exotic new physics effects that you can study by doing this, or for example, neutrino dark matter coupling, for example, as you're moving into or out of the WIMP wind, for example. So there's various new physics scenarios you could look for, but there are a few, for example, atmospheric scenarios you'd have to consider first before you were able to claim any discovery there.
Okay, thank you, Tom, for this very interesting talk. And it's also great to see that the students were so interested and asked many questions. Unfortunately, we have to move on, but we will have time. Say again?
Thank you very much, everybody. Yeah, feel free to, you can also ask questions on the Slack channel if you want, and I'll try to pick them up there.
Yeah, there were a couple of, I think, like 2 more questions about non-standard interactions. Maybe you can follow up on this on the Slack. That would be great.
No problem at all.